Today we are going to talk about these communication methods in embedded systems, and the main focus is on serial communication. So before moving to the serial communication, let's take a look at what is the serial communication against this parallel communication. So as you can see here, we have serial communication methods and this parallel communication. In serial communication, you have a sender, and both methods you have a sender and receiver. In serial communication, you have a single line or two lines, sometimes three lines, including the clock. But think about like using a single piece of wire. There's a sender and the receiver. You can send bits, one bit at a time, right? In parallel communication, you have, depending on number of bits, you have the number of wires. And so all the bits in the data will be sent at once, right? So it is more faster than the serial communication, because in serial communication, you have to send one bit and wait for the next bit to be sent using the hardware or the wire. Here, all the bits are sent simultaneously. So it's faster approach. So if you take a look at the differences, as I mentioned, in serial communication, one bit is sent at one time. So first you have to send this bit and it is received, and the next bit it is received, and likewise. In parallel communication, all the bits are put on the bus and then sent, and the receiver will be received all the bits at the same time. So both approaches can be synchronous or asynchronous. Serial communication can be synchronous or asynchronous. Synchronous stand for you have another wire which is generating a clock source. So even every rising edge or falling edge, you can send this data. That is, you have a clock system. So both the transmitter and receiver are agreed to the same clock rate, and so based on the clock rising edge or falling edge, you can send one bit at a time. So then so it is synchronized. And sometimes you don't need to have necessarily have this clock without by having a predefined data length. I mean, so here you can define this clock rate in hardware. For example, now this data is high and this data is low, and like this pulse, the duration, this time duration is known, right? So you will tell the receiver, okay, t is equals to a known value, and the sender is also known that is the known value. So if both of them are knowing this duration, so they don't need to rely on a clock pulse. So the transmission can be done, transmission and receiving can be done without any problem, because both the receiver and transmitter know the duration of the time period. So that is asynchronous. If you're having clock source, it is synchronous. So rising edge or falling edge of the clock, you can transmit the data. But despite in parallel communication, you will always need to have a clock. So during each clock pulse generated by the transmitter, the data will be sent. And so in this serial communication, it can be simplex, half or full duplex. Simplex means the mode is unidirectional. So you can only have a sender and a receiver in one system. So this guy can only send the data to the receiver. So this guy can only receive the data. That is called simplex. In parallel communication, you can be a sender and the receiver. So it's one-side communication. So always sender is sending the data and the receiver is receiving. That is known as the simplex. The half duplex is two-way directional communication, but one at a time. Okay, so assuming like you have sender and receiver. So by using single wire, like this guy can send the data to the receiver, so the receiver is observed, and so assume there's no another line, right? So in the next time, so this data is received, and the receiver can be the sender, and he can send the data to the this side. So this guy now become the receiver, right? So using the same wire, so at one time it can send the data to here, and in the next time it can send the data from this side to that side. So both communication cannot be done simultaneously. Either this guy can be a sender and receiver at one time. So once the data is sent, so if this guy wants to send the data back to this guy for some application, so he can stop. This guy can sending. This guy can stop sending the data, and this guy can now start sending back to this here. So it is two-way communication, but cannot be done simultaneously. But when it comes for full duplex, so this guy can send to this side, and this guy can send to this side simultaneously, right? So there should be two wires. So without having any interruptions or any dependency, this guy can be the sender, and this guy can be the receiver, and sometimes this guy can be the transmitter, and this guy can be the receiver. So the both communication can happen simultaneously. So it needs at least two wires for that approach. When it comes for parallel communication, it can be simplex, or it could be half duplex. Either this guy can send and this guy can receive, or either this guy can send and receive, and this guy can send, and this guy can be the receiver. Communication cannot be done in the both direction at the same time. That is why it is half duplex. So serial communication is simplex, complex design. So you need to deal with more sophisticated hardware, dealing with the dedicated hardware for that, which has the shift registers and all these things. Parallel communication is very simple. You just have number of wires, and you just put the data, and the receiver can update that data to a register. And so in serial communication, it could be sometimes 2 or 3 wires, sometimes 4 wires, but in parallel communication, depending on the length of the data, the number of wires going to be determined. So these are the major differences of the serial and parallel communication, but today our focus is mainly on serial communication. Okay, right. So let's take a look at these serial communication methods available in AVR microcontrollers. Since we have our focus is on AVR microcontrollers, let's take a look at what kind of methods that we can use to establish serial communication in embedded system using AVR microcontrollers. So it has the USART. USART stands for Universal Synchronous Asynchronous Receiver Transmitter. So it can either transmit and receive the data synchronously or asynchronously using a clock source or without the clock source, either in both directions. It could be simplex, duplex, or half duplex. And that is a old and widely used approach. So if you take a look at this ATmega328P microcontroller, so pin number 2 and 3 in port T is used for UART. UART is universal asynchronous receiver transmitter. So if you want to have the synchronous, there could be some additional pins, but I'm talking about the asynchronous. So by using TX and RX pins of this bit number 2 and 3, you can use this this microcontroller to communicate using serial approach. And the other one is SPI, Serial Peripheral Interface, and it is faster than UART. And so these pins are dedicated for SPI. So as you can know, like in order to program the microcontroller, also we are using this SPI. But sometimes there could be some additional sensors or microcontrollers or any devices which accept the SPI. So you have to use these pins and the hardware and the registers if you want to establish a communication. The final one is I2C or I2C, which is the inter-integrated circuit. So it has 2 pins, and it can be used to communicate up to 128 devices sharing the same bus. So it has a data wire and the clock. So it is a synchronous communication. You have 2 wires, one for data and one for clock. Here also we have, if you are not using the clock in UART, so that is known as UART, it is asynchronous. You can just use 2 wires and make a communication. You can use this TX and RXT to communicate with the UART terminal of any other devices. All right, so this is how we are going to interface your devices for communication using UART or UART. So here, the first one is synchronous approach, which is UART. And you have this side, we have this TX, the transmitter pin, and the receiver side you should have the RX pin. So this is data. So you have to interchange the pins, right? TX should goes to RX, and when this guy becomes a transmitter, it should be connected to the receiver side of this guy, right? TX goes to RX and TX goes to RX likewise. And if you need to have a synchronous communication, you have to connect the clock of this device to the clock of the other device. And you have to keep a common ground for both devices. Then you can establish a communication synchronously using a pulse based on the rising edge or falling edge. You can transmit the data which direction that you want to have. Like if you want to transmit, you can use this one. If you want to receive the data, you can use this line. And the other one is UART, which is asynchronous, so you don't have the clock source. So the RX pin of this device one goes to the TX pin of the other device, and this TX pin of this first device should goes to the RX of the second device. Like I said, is interchange. So this is the dedicated hardware available in AVR microcontroller for the UART or UART. And so these are the 3 pins. Actually, this is the RX pin and this is the TX pins. There's a clock pin as well if you want to use it for synchronous, but we are just dealing with the asynchronous. So think about this TX and RX pin. So in order to control the receiver, these are the hardware that is available, and the transmitter is controlled by using this section. And there are some other registers to write and read the data, but comes and transmit by this microcontroller. So it is full duplex operation. So as I mentioned, sometimes you can transmit and receive at the same time. And it could be master or slave clock synchronous operation. So sometimes this guy can be the master and generate a clock source, and the other guy can be the receiver or slave for the shared clock, which when it comes to synchronous. And this AVR microcontrollers offers high resolution baud rate, which is the bit rate. And there could be different types of serial frames, data, and the parity. So these things will be discussed in the upcoming slides. So I will go deeply what is meant by baud rate, data frame, and the parity. So up to now, you just focus on you have TX and RX pins and dedicated hardware, and there are some registers to control the operation of the USART. So these are the control registers that you need to understand if you want to deal with the USART or UART. So the control registers can be first used to determine whether you want the synchronous operation with the clock source, or you don't need the clock source and you're just using a synchronous operation. So by writing to the registers, you can determine whether you want the synchronous, which is USART, or asynchronous, which is the UART. And you can determine the number of start bits and stop bits, and the parity. Parity is to determine if there's a error in the data, and the number of bits in the frame, and transmission rate or the baud rate, and transmit or receiver flags and interrupts are all the things are controlled. This information is controlled by using these registers. So there are few registers available. These are the ones that you want to know. So every register ends with the number of N. In N stands for 0, 1, or 2, depending on the number of USART units available in the microcontroller. So some microcontrollers has multiple USART, which means you have USART 1, 2, 3, like that, 0, 1, 2, and like that. So if you're using USART 0, so the in could be 0, right? So you have to, this is UDR 0 if you're having on a single USART. If you're having another USART which is known as 1, so it could be 1. Likewise, depending on the USART that you're using, you have to change the N, right? So the first one is a UDR-N, which is USART input-output data register N. So that is used to transmit data buffer register, and USART receiver data buffer register share the same IO address, refers to USART data register or UDR. So which is like if you transmit some kind of data, so that is stored in this register, right? So it's a 8-bit register. So whatever the data you transmitted or received is stored here. So you can read this one and get the required data from your communication, right? So this is where you copy or download the data to this register, which should be transmitted or which is received from the user. And there are 3 registers. You see SR in A, B, and C. A is used to handle the flags and the status of the USART, and B is used to enable and disable the TX and RX pins. So you know, like this TX and RX pins of the microcontroller, sometimes you can just use them for these 2 pins. You can use them for digital inputs and outputs. But if you want to use them as for communication, you have to enable this TX and RX hardware. That's why we have this register. So if you enable TX and RX, those 2 pins are ready for transmit and receive. And the control register C is for to change the bits in the frame and the baud rate, etc. And for the baud rate, there is dedicated registers, UBR-RRNL and UB-RRNH, so which determine the speed of the data that you want to transmit. And now you can see the frame format. So this is the package of the data. So initially, so this is at high state. So typically logic 1, right? So this is logic 1. So this high state. So when there's no communication, so let's take a look at like this is a transmitter, and this microcontroller has a receiver. So this line initiated at a high state. So if it is a 5-watt line, so it is a 5-watt, right? So if you want to start the if you want to transmit any data, so you have to set this line to 0. So that is known as a start bit. So you have to pull the line down. So you will just put this voltage of this line to 0 by the transmitter. So the receiver now knows like, okay, it is now starting the data transmission. So that's how you know like there's a initiation of the data transmission. That is known as a start bit. So it's changing the state of this the voltage from high to low. And then you can have your frame, which is the data. You can go up to 9 bits. So 0, 1, 2, 3, 4, 5, 6, 7, 8. Together, including the 0, there are 9 bits. But most widely used approach is 8 bits. So like including 0, there will be 8 bits. Using this one also, it could be 9 bits, but most widely used approach is 0 to 7, right? So which is like, you know, like any register has like 8 bits up to 255. So that's why using 0 to 7, which counts altogether 8 bits. But there could be an optional bit number 8. For some application you can use it, but most of the time 0 to 7 will be enough, right? Which means 8-bit data. And then finally you have this parity, which is used to check whether there's a error in this data or not, right? So I will explain it later. And then you're going to stop the transmission of this packet. So then you just set this line to from 0 to high, right? So this is known as stop bit. Sometimes there could be 1 stop bit. Sometimes there could be 2 stop bits. If you're using 2 stop bits, that means like the receiver needs some time to start the receiving, get ready for the next receive. But most of the time, 1 stop bit will be okay. So the other stop bit, if you're using, it will be neglected. And again, if you want to start sending new packet, again, you have to set the line down. And or if you don't need, you can just keep the line high. Right. So that's all about this frame format. Basically, the most widely used approach is having a single, you always have 1 single start bit and 8-bit data and 1 stop bit, right? And sometimes you can use a parity, or sometimes you can skip the parity check. So the parity is used to determine whether the transmitted or the received data having no issues or having any issues. You know, like when you transmit a data packet using a wire, like you have this transmitter and the receiver, and perhaps you have to send it for long distance. And sometimes when you cabling this, there could be some electromagnetic interference or some sort of noise coupling to this one. So you just send 1, but due to this electromagnetic interference, so that bit may be disrupted. So that this bit, you send it as 1, but due to some electromagnetic interference, so it became 0. So you know, like your data is corrupted. So in order to determine that, you just use additional parity bit. It could be high or low, right? So so it is a parity bit. So in order to generate the parity, so you have to use tell this USART you are using parity, which means your system is capable of determining there's an error in the data. So you have to use this PMN1 bit in UCSRN register, which I told you. And so this is how you're going to use it. Before comes to this one, so I would like to explain you what is parity in detail. So now you can see from this slide, this is your data. So yeah, I have used 7 bits, right, for the ease of the use. So you can see like there are 7 bits, 0, 1, 0, 1, 0, 1, and 0, right? So there are 2 ways of determining this parity bit. One method is even parity, the other one is odd parity. So if you use even parity, so what you're going to do is, so you just check number of ones here, right? So it is 1, 2, 3. So 3 ones are just is an odd number, right? So you just so this is your additional extra bit that is going to be used as parity. So you make the parity bit to 1. So including the parity, so now you can see 1, 2, 3, and 4. All these ones in this data frame are now when you count them, it should be even number. That's why you call this as even parity. So if you use the odd parity, so just take number of ones here, 1, 2, and 3. So it is already odd number. So so you just put 0 here, then you know, like including the parity bit, number of ones here is odd, right? So that is how you determine the parity. But when it comes for the microcontroller or the AVR, so first thing is you need to enable the parity. If you want to use the error check, you have to enable the parity by writing to this 2 bits in this UCSR NC register, right? So if you use by default it is 0, so which means parity is disabled, and this one is reserved. You can't use it. And if you want to set it for even parity, so you have to set this bit high and this bit low. And if you want to use the odd parity, this both bits should be set to high. And so this is not done by us, right? When the programmer doesn't want to rely on the parity check, so he doesn't want to count this number of ones and make this bit here. So it is all done by the hardware, right? So when you enable, so the hardware will add this parity bit to the end of the frame, right? So this is done by the hardware. So you just need to enable this bit, so then the rest will be done by the hardware. So the hardware, so what they are doing is just XOR all these bits here. Take all these bits and XOR, and if you're using even parity, XOR with the 0, all the bits XOR with the 0, and use the odd parity, XOR all the bits with the 1. So you have say 8 bits, so all the 8 bits will be XOR with the this 0, 1 depending on the parity. So once you receive the data packet, so if there's a distortion, so you can determine the parity. So which means like let's say now you send this data sequence, right? So some kind of electromagnetic interference or some kind of EMI issue, which is export your cable, it's transmitted using a cable, right? So all these zeros and ones will be transmitted using a cable due to some electrical noise or EMI. Let's see, this bit is used supposed to send it as 1, but it is now became 0, right? So you just want to send it as 1, but that database is corrupted and you received 0, right? So you received 0 here, but the parity bit is unaffected. So the parity bit is so you assume you use even parity, and this is your bit sequence. You expected to have 1 and the even parity, and so like your parity bit is now 1, which means there should be a number of ones you count it, right? 1, 2, and it should be a odd number. The number of ones in the data frame should be an odd number, because including the parity bit of 1 should be an even number. Now you see, like, it is 2 ones, right? There's no that is an even number. So which means like there's something wrong in this data frame. So either this bit is destroyed, or this bit, or any bit somewhere, like due to some kind of issue, there's something is wrong, right? So like you should ignore that data packet, right? So you can ask the receiver, okay, there's something wrong, can you resend that data packet? So then you can just receive a correct data packet again, right? So that's how you're going to deal with these errors in the data frames by using the parity. So that can only determine single bit error, which means like if one bit is destroyed, you can easily determine. But if 2 bits are destroyed, this parity cannot check. So it will give you a false. If these 2 bits are destroyed, the parity will be the same. So it will tell, okay, this frame is okay. But in reality, 2 bits are destroyed because the system cannot detect 2 bits errors. So in order to have more and more bit errors, you have to use a more sophisticated hardware that is out of the scope. For single bit errors, you can use the this even node parity. That is more than enough in real world applications when you're transmitting for short distances, especially in embedded systems. But when you're using long communications like RS-232 or any other format, if we are vulnerable to more data issues, you can use 2-bit errors and a number of bit errors, but that is out of the scope of this lecture. Right, so we have discussed the parity check. Like you have to enable these bits depending on the type of the parity, then all done by the hardware. So if there's an error in the frame, so UPEN parity check error will generate a flag and telling there's an error in this the received data packet. So you can just ignore and request the transmitter to send a new packet again. Right. So any data packet should have a transmission rate. So in USART, we call it as baud rate. So in USART, the baud rate is equal to the bit rate. So baud rate not necessarily to be equal to the bit rate, but in AVR, so we normally call the bit rate as our baud rate. So in order to make a reliable connection, or your transmitter and receiver should be handshake for the same speed of data or the bit rate, right? So that is the how fast you send in these ones and zeros. Like, let's say you have like 8 bits here, sent for 1 second. So that is your speed of the data. Sometimes you can send 16 bits, 2 packets of data per second. So that is another speed. Likewise, the speed of the data packet is known as the baud rate. And so the most commonly used baud rates are 9,600 and 115.2K. So that is bits per second. So if you having a transmitter and receiver, so you don't know the what is the baud rate here. So you can the receiver, you have to adjust your receiving speed or the baud rate. You can just put 9,600 if you are not sure about what is the baud rate here, or 115.2 here, and you can check whether these two for these two baud rates you can obtain the data without any issues, because if you are not sure, these two are the most widely used approaches, so it should work. Otherwise, you can try all these other baud rates until you get the correct data packet. When you don't know one side, the baud rate of one side. So as I mentioned, so the baud rate should be equal for both devices. So you have to set the baud rate by writing to this UBRR in register of the microcontroller. So that's the equation for that. First, you need to know your system frequency, your CPU clock speed, and then this baud rate. So if you want now 9,600, you have to substitute this as 9,600 multiplied by 16 minus 1. So that is the required value that you should write to this register. So if you get any value that you should write to that register, then that particular baud rate will be set by the hardware. If you know this value you written here, then you can determine the baud rate by using this equation. That is something that you can reverse calculate and see what is there, right? Sometimes you cannot directly get any value, like there should be some values in between. So there's an error percentage. So that is, I'm not going to talk about that thing much, but remember, so if you want to use a particular baud rate, so you just substitute it here, multiplied by 16, and you should divide your clock speed by it, that value, and minus 1. That's the value that you should write to your UBRN register in order to achieve the particular baud rate. All right, so before you start the communication, so you have to write the correct values to the required registers. So first approach is to initialization of the USART. So first you have to do these settings. Number one is the baud rate. So the baud rate can be adjusted by using the correct value to the UBRR0L and UBRR0H registers. If your clock system clock frequency is 1 megahertz, and if you are using 9,600 of baud rate, the required value that you should write to UBRR0L is 6. This is your first step that you should do to initiate the USART. So I can show you the how this registers using the data sheet. So if you want to determine which is the value for that you should write for UBRR in register, so refer to table number 20.4 in section 20.10 in ATmega 328P microcontroller. So since we are for this example, I have used the system frequency of 1 megahertz, and the baud rate that I'm using is 9,600, and my system frequency is 1 megahertz. So this is the value that I should write to that register. All right, 6. So that should be written to UBRRN register. Okay, so if you want to have different baud rate, so the required value can be determined, is given in this table. So this table has only values for predetermined system clock frequencies. But for you can see 16 megahertz and 8 megahertz. So these are the typical use clock frequencies. So you don't need to use that the equation that I have shown. You can just refer this required value. Then so you can move to this UBRRN and H register. So if your value is like less than 255, you just need to write to this lower register. So that can be so this register has 11 bits, right? So if your value is ranging from 0 to 255, you just need to write to this lower register, right? NL. And if you use values more than that, you have to use both registers. But most of the time, it is okay. It will be some value less than 255. It is okay to write to UBRR in L register. So since I'm using system frequency is 1 megahertz and 9600, so the required value I should write is 6. So I can just go to here and write set this UBRRNL as 6 because it is less than 255. The next one is you have to adjust this frame format. So that can be done by writing to UCSR0B register. Okay, so the baud rate is now set, and the next one is to determine your frame format. And normally we are using 8-bit data, and you have to enable this TX and RX pins for data transmission and receive in the microcontroller. Like I showed you in at Mega microcontroller, there are different pins for dedicated USART. So for USART 0, so pin number 2 and 3 is there. So you have to tell the microcontroller we are using these 2 pins for communication. Otherwise, these 2 pins can be used as a normal digital input and output. But if you want to enable the transmission and receive, you have to set these digital pins for the TX and RX, right? So that should be done by writing to UCSR0B register. So this is how it looks like in UCSR0B register. Now, so like I mentioned, so the thing is you have to determine whether so this is this register UCSR0B, and so if you want to enable the receiver and transmitter, bit number 4 and 3 RX enabled and TX enabled should be set high, right? So 3 and 4, like this is the transmitter enable bit, you have to set it high, and this is a receiver enable bit, so you have to set this to high, which means this TX and RX pins of the microcontroller, which is normally used for digital input outputs, now are set for USART. And the next one is character size. Like I mentioned, so we are normally using 8-bit of data. So in that case, if you want to use the 8-bit data, normally you can do is set this bit to 0, right? And these 2 bits to high, that is in UCSR NC, right? So because 1 bit is used in UCSR0B, if you're using 8-bit together with this bit 2 here, right, in this register, register B, and together with the other bits in the register C. The next two bits are in here, register C, right? All three bits must be considered if you want to determine the bit size. So if it is 8-bit, this bit in register B should be 0, and these 2 bits should be 1 in register number C, right? So if you want to use 8-bit data. The final one is you have to enable the transmitter and receiver depending on the usage. Right, so the frame format should be set together with this 0B and 0C registers, like I mentioned. So these 2 bits should be set high, and this the other bit is by default is 0. So that is set for 8-bit data. And the enable of the TX and RX is done by setting these 2 bits in this register, so which I have just explained. And the other major things that you have to consider is whether your operation is synchronous or asynchronous, and the parity. If you're using even parity, you have to set that parity bits, and the number of stop bits likewise. So that is determined by UCSR 0C register. So now you can see this UCSR C register. So since we are using UART, right, asynchronous operations, so we are not using a clock source. By default, it is 0. So these 2 bits are by default 0. And so if you want to use the even parity, so UPMN1 and UPMN0 should be 1 and 0 respectively. So it should be 1 and this should be 0. So if you don't need the parity, you can just left them by default values, that is 0. And the number of stop bits by default is 1, that is the recommended one. So you can just leave that is by default value 0. And since you were using 8-bit data frame, so that is these 2 bits should be 1 here, right? These 2 should be 1 because we already kept this guy 0 according to that table. So so the synchronous and asynchronous operation is determined here, and the parities can be determined using these 2 bits in, and this number of the start and number of the stop bits is here. Number of the start bit is always a 1, and character size is determined by these 2 bits in this register number C. Okay, so that is all you need to do to initialize the USART. Right, so normally you can use the USART without using the interrupt service routine, but if you wish to use the USART interrupt service routine, you have to disable the global interrupt flag. So then you should done this initialization. But so all these materials is based on without using interrupt, so you don't need to worry about. So if you do these settings, the writing to the correct values to these 3 registers, I think you are all good to go, right, without having an issue. So your USART is initiated for data transmission and receive. So let's take a look at how this data is transmitted or sending frames. So first is the data transmission is initiated by loading the transmit buffer with the data to be transmitted. So which means like you have 8-bit data, like let's say like you have this data frame. So that is useful data. I mean the 8-bit, that is the data. It could be something that is read from an analog channel or PWM speed or anything, right? So any value. So that data, the bits, you have to write it to this UDRN register, transmit register, right? So that could be like a some value that is you written for a variable. Let's say like variable A is equals to this binary value 0B 10 11 1000, right? So that is your data. Now you have to copy that data, the required data in your any variable to this register. So that is the input output data register. So that should be available. I mean, like this transmit register should be ready to accept any data. Otherwise, you cannot write it. Right. So then the this one is checking whether this there's a shift register, because the data should be transmitted 1 bit at a time, right? So there's a shift register. So once you copy that data to here, so the required data will be moved to this shift register. So the shift register will shift that data, copying it to here, and starting from the this least significant bit will be transmitted first, right? So this one will be transmitted first from the outside of this the TX pin 0. That is your first. You have the start bit 0. This was your idle state, and then your first data bit, that is the LSB, that is transmitted. So the shift register just shifting these bits to the other side. So the shift register should be free. I mean, like you cannot just transmit this data to the shift registers when it is doing any ongoing data transmission. So this guy has to be waited until the ongoing transmission is completed. Once any transmission is completed, just copy that value to the shift register. So the shift register will move the bits from the output of the TX channel by adding this parity bits and stop bits and everything on top of your data. So that is how you send in the data. So all you need to do is just load this whatever the data you want to send to this UDRN transmit input output register. So the rest will be done by the hardware. So now we can take a look at to send a frame. By referring to this example code, right? So here I have defined TX buffer is empty. So that is this UCSR0A register and this bit UDRE0. So you have to check whether this bit is true. So that's why I'm taking the AND. So when you're taking this AND with this bit in this register, you are just checking this bit is set. If it is true, only this variable will become high, right? So I can show you how this works in the data sheet. Right, so now I'm referring to the data sheet. So this is UCSRNA register, control register A. So you can now see UDREN. So USART data register empty. So UDREN flag indicates the transmit buffer UDRN is ready to receive new data. So you can remember like this is the transmit input output register, right? So it shares the same address for receive and transmit. So like I mentioned, so you had your data. So you have to copy that data to this register, right? And the thing is, before you copying it to this register, you have to check whether this this bit is when this bit is true, only you can write that your whatever the data variables to TX and RX data register. Okay, so you have to go to register A and check this UDREN. If this flag is set, means now this register is ready to accept your data. So that is what I have done in the code. So now once I check that flag, so I know like I can now write that my data to that data register. So the setup function will be the same, all the things that I have previously mentioned, the red settings and enable of TX and RX, synchronous, so parity, and the number of bits in your data should be initiated by writing to these three registers. And now if you want to send any data packet, so this is the function that you can use. So void start transmit. This is any arbitrary name that you can use. And I use unsigned car data. So this is the data that I have in my hand, which means like any data that came from ADC reading or PWM or any process data for any operation in your code is moved to this function. So once you move that data, so it's just checking whether this flag is set. If the flag is set, then whether if it is true, then you can put that data to here, right? So that's how you're going to deal with transmitting the data. So there was a slight mistake here. So this should not be the if this should be while, which indicates like as I mentioned. So this bit should be high. It should be set to high if you want to write to UDR0 register. So which means if there's an ongoing data transmission, so this bit should be at 0, right? When this UDR0 is busy, right? So which means this is busy means 0, and not of taking not of this one is 1, right? So if you take not, that should be 1. So this while loop will be activated. So while 1 is just waiting because this is now busy, right? So once it is ready, that will be set to 1, which means this is becoming 1. This will become 1, and this will become 0. So the while loop, the program will exit from the while loop, and then it knows like that UDR0 is ready to accept new data. Then you write that whatever your data, copy to UDR0 for data transmission. Okay, so that is how you deal with transmitting the data. So once you copy that data, so the rest will be done. So that it will, if the shift register is not busy, so copy to the shift register and move the data bits out from the TX pin. Now we are moving to the receiver side. So in the receiver, so the receiver starts data reception when it detects a valid start bit. So for your receiver pin, once there's a data is coming, like initially it is on high state, and This is your start bit. Pull the line to 0. So when the valid start bit is detected, so the receiver is activated. So each bit that is follows the start bit will be sampled at the baud rate and shifted into the receiver shift register until the first stop bit of the frame is received, right? So then you have your data, ones and zeros coming from this side, all this data, and then the stop bit will be high state. So until the stop bit is received, all this received data will be moved to this shift register. And normally there should be one stop bit. If there's another stop bit, that is ignored. So then once this first stop bit is received, complete serial frame is presented in the receiver shift register. So all the data is copied to the moved to the shift register one at a time. The most significant bit is stored here, likewise. And then that will be moved to the receiver buffer, right? So there's a receiver buffer. So then this is the receiver buffer. So then if this your UDRN received data register, if it is ready, then it will be copied to this one. So you can, if you just request the data from the UDNR0, so that will be, you can receive the received data from this location, right? So you just need to read this UDRN received data if you know there's a data packet is received. So now this is a simple code example. Here I have defined RX buffer is full by writing to the US register A and RX0, RXC0. So which means like a start receive is completed. Now you can see from the data sheet. So this is that the one that I'm talking about, bit number 7 in US UCR NA 0A register. This bit, right? So if your data is received, the receive is completed. So this bit will be set to high. Initially it is 0. If the data packet is received, this will be set to high. So you can check this bit. If it is 1, you know, like your data packet is ready. Then you can request the data from this this right into the input-output register. Okay, so you can request from the UDRN read register. It has the same address as the transmit register. If you read this one, so that you can read the received data. So that is basically you are just checking this, the receive is completed by checking this bit. So the setup function is same. So we are using the same baud rates. And so this is how you're gonna get your data, right? So you can just call this function, right? For example, let's say now you have a variable called a char variable, let's say data. So you want to, this is your variable in your program, char data. So you just need to update your data with the received data packet. So you can just type, call this function. So the function will return UDR0, the received data packet, the value. So you have to just keep waiting until this buffer is ready, right? If it is 0, which means there's nothing is received, right? So which means not of that is 1. So while loop will be continuously looping here until it is ready. So if the data packet is received, that is, this bit will be set, and it will exit from the while loop and return this UDR0 value, so that you can copy it to your whatever the variable that you are interested on your program by calling to this function. Right, so we can you can try a simple simulation example. So simulation platform, you can use the Atmega 328P, and there's a virtual terminal. So in here, so these are the pins in Atmega 328P version. So in the simulation, that TX and RX pins goes to 30 and 31 in this package, right? This is, I think, a service mount package. The pin numbers are slightly different from the through-hole one. That's why we have 30 and 31 for TX and RX. So your RX should be connected to the TX of your virtual terminal, and RX of the virtual terminal should goes to the TX of your microcontroller. So then this is how you set. So all this data received and transmitted can be viewed from this virtual terminal. So if you type anything here, you can just type and press enter, so it will go to the microcontroller. If you write any code to transmit any data, so that will be displayed in here. Now this is a simple example code written for receive and send data using Atmega 328P serial port. Right, in this code, I have used my CPU clock frequency as 8 megahertz. And if you are using the simulation in here, so you have to just double click this one and keep this clock division 8 to set it to 1 on program. Then so it will accept the 8 megahertz clock frequency. If you just remember, like a double click, and when you import the X file, set this clock division to on program, which means so it is accepting 8 megahertz for the clock frequency. And so I have to include AVR input output header and card data, and this is my set of functions. So I am using 9600 baud rate at 8 megahertz system frequency. So 0H register should be 0, and UBR0L should be 51. So those are the settings that I have to do, and I can show you. This is on that table. Here you can see this the baud rate that I'm using, 9600. System frequency is 8 megahertz, and the required value is 51. The reason that I'm using 8 megahertz, you can see like there is an error percentage. So for 9600 baud rate, if you're using 8 megahertz system frequency, the error percentage is 0.2%. But if you're using a 1 megahertz, so 1 megahertz, that error percentage is -7. So that is quite large, right? So in my previous example, I have just written 6, assuming system frequency is 1 megahertz, but the error percentage is -7. So that is quite large. Sometimes, like the internal oscillator is not accurate than if you're using compared to crystal oscillators, external crystals. So since we are doing the simulation using internal RC oscillator, which is not quite accurate, so this kind of error percentage might be troublesome. So sometimes it won't work. So in that case, I have used internal 8 megahertz without having that clock division factor by 8. So which means I'm using internal 8 megahertz oscillator available to my CPU. And if I use 9600 baud rate, so the required value should be 51. So the error percentage is 0.2, so which is very low, which means my data transmission is quite reliable. Now you can see, this is the rest of the code. So I have used no interrupts, and TX and RX are turned on, and 8-bit data. And so I have set it for synchronous operation. And here I haven't used parity, so it's no parity. And one is topic and 8-bit data. So I have 3 functions here. The first one is to transmit a character. So you just copy your character to this function, so it will transmit that character from using here. So just waiting until this UDRN0 is ready, and then copy that your character to UDR0, and rest will be done by the hardware, so it will transmit the data. And if you want to transmit a string, like some kind of a string, then this function can be used. So it is based on using pointers, and this function is to receive a character, right? So it returns the character, and same example that I have explained, returning the value of UDR0. So this is my main function. So it comes to the setup. So setup is to initiate the USART, and I will write it. I will call this function USART TX messages, so I can transmit a string, right? So I'm just typing initializing the USART. This is my string. You can write your name for this, even it doesn't matter. So that will transfer all these characters in this string using the TX terminal. And so then I have to go to the next line. So I mean, like, if you don't use this one, the next data string will be starting from the end of the T, right? But I want to have a new line, so then I can use this 0D, which is a carriage return. So for the next line, so here that I have used the TX function, so because I'm just sending one byte, right? So I'm using this function. It will transmit this 0D, which is for representing new line. And then I'm just typing hello world in another string. So here you can use, without using this one, you can just put the /n and /r, then it will be simply do the same job as character return, right? Without having, because the next line will be start from the without having this command, right? So these two is equivalent to this one, right? Which means you don't need to always type this command. So if you type #n and #r, so the next, it will jump to the next line. The cursor will be moved to the start of the next line. Then I'm just waiting in the while loop. If I receive any data packet, so that is copied to my data. It's a character variable, and then I will type this symbol using this one. So then I will send the same data that I received back to my virtual terminal, and with a new line. It's basically like whatever the data I received, I will just send it back. So here in simulation, you can type any character like A, B, C, O, 1, 2, 3, or anything, and then type enter. So it will read this one, read and copy to this data variable, and it will transmit this character, and to show you like sending it back, you can skip this one if you want, and then transmit this the received data back to the virtual terminal, right? So you will receive like whatever you type will be will come back and display in your virtual terminal. So now you have seen like this kind of carriage, the characters, right? So that is because we are using ASCII, right? This is the ASCII table. So like if you want to send capital A, so you have to send 65, right? So you can't type capital A. So you have to send the ASCII value to 65. If you want to have a new line, so you have to send like hexadecimal 15 or carriage return. So that is what I did here. Okay. So if you want to the point message, it will be okay to be sent. If you want to send a single character using here, if you want to send, for example, now let's say you want to send capital M, you have to either type decimal 77 or hexadecimal 40. So you have type 0 hash 40, then it will transmit capital M. So the ASCII value will be transmitted, but it will be displayed using the human readable version, right? The virtual terminal will show you the represented character by decoding it, right? Make sure you transmit the correct ASCII code if you want to send data. So that is all about to deal with Atmega microcontrollers or AVR microcontrollers. So this code will be helpful for you to work on your projects. Remember and understand how to initiate this the USART and how to select the correct baud rate referring to the datasheet, comparing to your internal clock frequency. And this is how you're going to transmit a data a byte, and this is how you receive a byte, and this is how you transmit a string, right? And remember that you are transmitting ASCII values if you just transmitting a single byte, but for characters string, you can use this function, so you can transmit this whole string without having an issue. So previously we have seen like how to program Atmega microcontroller to initiate USART. Sometimes that the codes that we have already discussed could be used to communicate with external devices, sensors, or communicate into another microcontroller. But now let's take here. I'm going to show you how to make a communication with the computer using the serial port. So the first method is to use the serial cable and level converter. So some old-fashioned computers have a serial port in the computer. So it looks like this, right? So you have to use a serial cable, and so that the voltage level accepting by the the computer is oscillate between minus 12 and plus 12. So the signal will be something like this. So so this is 0 volt, and the low level is minus 12, and the high level is 12 volt plus 12, and it oscillates between minus 12 and plus 12. So that voltage is not cannot be directly connected to a Atmega chip, because Atmega is accepting only 0 to 5 volt, right? So if you provide this voltage, so this port will be damaged. So in that case, you need to have a level converter. So max 232 chip is used, so it can be powered with the 5 volt, and so it will convert like whatever the data that you're sending here, any voltages from 0 to 5, and convert it back to minus 12 to plus 12 using this capacitor, switching capacitor converter, when whatever the data received will be processed and sent back to convert into 0 to 5. So that's why you need this level converter max 328 232 to make an interface between the voltages. And the other method is using USB to serial converter. You can see this is like most of the new computers does not have this serial port. Instead, they have the USB port. So you can connect to the USB port, and you have to use the interface, that is the USB to serial converter. So this is your Atmega chip. So it sending and receiving data using this USART terminal. And you have to use this FT328RL USB to serial converter. And you have to connect this RX of your Atmega chip to the TX of the converter, and TX of the Atmega chip to the RX of the converter. And the ground of the both circuit should be common. And then you can use, by using a USB cable, you can connect it to the computer. But make sure you have to install this driver for this one, downloading to your computer, then it will be recognized by the computer. So whatever the data sent and received can be communicated to the computer. So this is the most widely used approach nowadays. Right, so let's take a look at this FTDI converter. So it has two forms. The first one is which comes with this cable connector, right? And the other one is comes with the USB port with this kind of connection. So here you type A connector, so you can just plug this side to your computer, and the converter is inside this this chip is inside, and all the circuit components are embedded close to this USB terminal, the connector. And the other side, the return side, you have this ground, VCC, TX, and RX, right? This arrow terminal indicates the pin number 1, which is the ground. So you can connect your TX and RX to your microcontroller, and this side goes to your computer. And if you use this type 2, which is you have to use an additional cable because it doesn't have the cable. So type C USB cable should be connected to your computer. And here you can use the TX and RX and VCC and ground. So this is how you connect to your microcontroller AVR chip. So you need to use VCC, ground, TX, and RX. TX goes to RX, RX goes to TX, and ground are common, and VCC is connected to your microcontroller. You can take the power from the USB terminal. So the USB has 5 volts, so that can be given to your microcontroller as well. You don't need to use any external power supply to power your microcontroller. Then you can use it for your purposes. Right, so if you plug this one, so you have to install this FTDI driver. So if you now, let's say like you have written a test code to write like a hello world string that you trying to send it to your computer, right? So you now just plug into the USB. So in order to open this virtual terminal, you have to download another software called Putty, right? So if you download, and you can download it from the internet and install. So if you open this, it will be the window will be like this. So here you have to just go to serial, and when you click this, you have to find the correct COM port that where your USB is connected. So you can go to device manager in Windows and figure it out. The FTDI driver is installed to which USB port, and you can see like FTDI drive is detected to COM port number 3. If it is COM port number 3, select the COM port and configure your baud rate in your computer, because you can write your program to which the baud rate and start and stop bits, like I mentioned in this code, right? Baud rate settings and stop bits and parity and everything. This is the settings that you have done in your microcontroller, but your computer should always should be know the required data settings in your microcontroller. So in that case, you have to adjust these parameters. So you have to set the baud rate and data bits, stop bits, and the parity with the even parity, no parity, and set the flow control to none. And if you write a hello world function sent by your microcontroller, if you set it all the things correctly, you can see that from this virtual terminal, right? And if you want to send the data back, you can just type in the virtual terminal and just enter, and you should be able to receive in your microcontroller by using this function. And you can send that data back to the virtual terminal and see whether the code is working, right? One thing you can do without using a microcontroller to see like this part is working, you can just plug this one to the USB and short circuit this TX and RX, right? Short circuit these two. Okay, here short circuit these two. So then by short circuiting, you just making the transmit and receiving share the same line. Then if you type any character and press enter, so it will be bounce back here, right? If you type A, then it will be come back to this because it is read, just repeating back and read by this your computer. So you can see like this FTDI is working and the party is working with same setting. If I just short circuiting here without using a microcontroller, right? You can see your FTDI drivers and this one is working and the party is working by short circuiting this one without having a microcontroller, without using any code, right? If you want to do test coding, you can just use a microcontroller and put into a breadboard and connect it to the FTDI driver and connect into this configuration. And using the party, you can work on just play with this coding. So you can just order this one from any vendor from the internet. Even I think there could be some domestic suppliers who are selling this product. Now, when you're using Arduino, so the things will be much easier for you. So you don't need to deal with these complicated registers. So all you need to do is if you want to make a communication between the computer and the Arduino, so just plug your Arduino to the USB port and go to the tools and select the right port, and then you can obtain this virtual terminal, which is for serial communication, right? So like we did for using this PuTTY serial console in the Windows, the Arduino itself, it has the Arduino IDE has the serial communication console. So you can transmit and receive the data. Make sure when you write in the code, so you have to adjust this the correct power rate, and then everything will be set, right? So you can transmit and receive any strings or any characters. So you have to have some background and understanding about the functions that is used for serial communication in Arduino. So the first function is serial write. So that is to write binary data to the serial port. This data is sent as a byte or series of bytes, right? So there are some syntax. So serial.write the value, and serial.write the string, serial.write a buffer with a specific length, right? So the parameter serial is the serial port object, value is the value that is in a single byte, string is a string of bytes, buffer is the array, length is the length of the buffer. And sometimes you can take the return of these functions, the number of bytes sent, right? So I will show you a few examples. So now this is using serial.write function. First step is to, in your void setup, you have to initiate the baud rate. So I have set it to 9600. Make sure you do the same adjusting in your COM port when you open this Arduino COM port. Keep it to 9600 as your code. And if you type serial.write 65, this is the value, and that is represent capital A in ASCII. You can see, like, if you go back to this ASCII table that I have shown you, For capital A, it is 65. Okay, so if you send 65 as a value using serial.write, so capital A will be displayed in your serial console. And if you want to start a new line, so you have to type write 10, serial.write 10, so it will move the cursor to the next line. And so if you want to send a string and the count the number of bits sent, so you can use the serial.write the hello string, right? If you don't use this one, you can just send this serial.write hello, so it will display the hello. If you copy that this function into a integer and a variable called bytesend, any variable like integer, data, or bytes, or integer into like a variable name could be anything, right? ABC or anything. So that will update this variable with the number of bytes in. So I have sent here like 1, 2, 3, 4, 5 for hello. So this byte set will be updated. This variable will be updated as 5. Right. So you're just copying while you send in the data. And I will make a new line, and then I will use this serial print function. So for the moment, just assuming it is nothing, right? So I will explain what is serial print. But if I want to show this variable is updated, I can display this bytesend variable and send it to the serial port. So you can now see it is 5 will be shown in this serial port, right? That is just to demonstrate like this variable is updated with 5. And I have make a new line. So all the time you don't need to type this 10, right? Instead, you can type #n and #r with this string. Then it will jump to the next line. But remember, like in this case, the number of, if you use this one, the number of bytes you sent will be 7, right? Including #n and #r. Hello has 5, and this n and r has 2 additional bytes, so that is 7. We use this function that now the variable will be updated to 7. And if you want to use this function, serial.write buffer and length. So I have make an array. The array type is byte, and the array name is my data, which has four numbers, 4 bytes. Like this is 48, 49, and 50 and 51, which is in ASCII representing 0, 1, 2, and 3, right? So if I want to display 0, 1, 2, and 3, the ASCII value is 48, 49, 50, and 51. So I just type serial.write my data. This is my buffer, and I just want to send the first 2 bytes, like 48 and 49. So when I send it, so the ASCII value is sent and converted back. So it will be displayed is 0 and 1. That is shown in here. So this is how you're going to use your serial.write function if you're using Arduino IDE interface. Now let's take a look at the serial.print function. So it is print data to the serial port as human readable ASCII text. So whatever the format that you send, it is human readable. For example, if you type serial.print 78 will be displayed 78 in your serial port. If you type serial.print floating value 1.23456, it will only show up to the 2 decimal points, 1.223. If you print serial.print capital N within this quotation marks, so it will display the capital N as a byte. If you want to display hello world, send it within this quotation marks, so it will display hello world. You can serial.print a value, any variable parameter that in your code using this serial.print function. And you can use the serial.print and return the number of bytes written through this, like I mentioned in here in the previous code. You can update the number of bytes set using serial.print function if you wish to have. All right, now I'm going to show you two examples. So the first example is read and print characters using Arduino Uno board. So here you have to plug your Arduino Uno board to your USB port. And in this example, so there's a dedicated LED on your board which is connected to the pin number 13. So if I type capital H in my serial port and send it capital H, the LED will be turned on. If I send capital L using the serial command window, so the LED of the Arduino board will be turned off. So this capital H and capital L are read by the Arduino board, and the LED will be controlled accordingly. In my void setup function, so I set this pin number 13, which is connected to the LED as the output, and initially I have turned off my LED, and the serial communication baud rate is 9600. For testing purposes, I have used serial.print function. So in order to show you how this works, right? Serial.print. So if I send serial.print capital A within brackets, it will display capital A. And if I want to start a new line, the next one, so I have to send 10. And here I have sent 97, which is simple A. You can see with the new line, if you don't use this line, the simple A will be just after capital A in here. But with this new line, it will be down in a new line. And again, I have sent a new line to initiate that. So if you type capital H here, if you type capital H and press enter, then it will be sent through the serial port to your Arduino board. So there are functions to read that one. So the first in your loop, this function is checking whether there are some data received in your serial port in your microcontroller Arduino. So you have to use serial.available. If it is true, it is higher than 0, which means data is received. Data are received. So you define a char variable on a C, and you call this serial.read function. So that will copy the data received from the serial port and update to this variable C, right? And so if I type capital H and send, so the variable C will be updated with capital H. Now you can use these two functions. So if this variable C that I have used here is equals to capital H, this is how you're going to check whether it is equal. Capital H means C variable is exactly equal to capital H. So I will set my LED to 1, which is LED is turned on, and I will just send that received data back to my serial port, because I can now see like capital H is received. Here I have typed H and enter, so it will be disappeared. But while turning on the LED, I can bounce that whatever the data I received back to display on the serial port, so you can see capital H. And I will make a new line here. So if I type capital N and capital L and press enter, so that C variable will be updated with capital L. This one will be updated with capital L. So now it will jump to this function. So C is equals to capital L, then the light will be turned off, and I will just copy that the value in this variable back to here. So that is capital L. and I will make a new line. So this is how you're going to read and write data. Especially this is reading and make commands, so I need to deal with the serial port. Okay, now this is the second example, read and print strings using Arduino Uno board. You can see here the serial.begin function. So the initially this baud rate set to 9600, and I have typed serial.println. Print line is starting with a new line again. Hello world. So this is what you just see when you power up and when you do this coding, right? And so you can type anything here in your serial console. And if I type hi there, and you have to press enter, so it will be read by this program and send that data back to your console to display here. So this is what I'm typing, and this is what I'm just received, and send it back to display what I have, what you have just typed. So here I have defined a string, which is known as message, and empty string. The string name is message, and it is an empty string. If serial is available, which means if you type any data and when you press enter, so the data will be sent to the Arduino. If the data is received by the serial port, this will become true. So you have to keep reading because it's a string, right? There could be several characters. So if this at the end of here, so there won't be any character, so you can type a while loop. While this all the data is read, it will be in this while loop until it is read the last character, and the message plus minus character read from the serial.read. So it will update this message string one at a time, copying the character that you received from here. So the H will be go first, and it will be read, and this serial.read will read this H and update it the string, and then it will update read the I and update to the string. Likewise, keeping a small delay until this user get ready. And once you update all this string until the last bit is received, once everything is done, you can this will skip from the while loop because all the data is now read. Serial.l will become false. Then it will comes to here. Then you have serial.println, a new line with this the message string. So whatever you have typed here will be displayed in your serial console. So that is how you're going to read and represent strings if you use Arduino Uno. So that concludes this serial communication lecture. So I hope you have had the basic understanding about how to use these registers if you're using Atmega microcontrollers and if you're coding with Atmel Studio. But if you're using Arduino Uno, the things will be much easier. You can deal with this readily available functions dedicated in your Arduino Uno libraries. So it's all up to you. If you wish to do the projects in Arduino, you can prefer these functions. An example that I have discussed here. But if you work with complicated projects with Arduino, AVR microcontrollers, and if you're dealing with Atmel Studio, remember to understand this required registers and how to initiate the USART and how to work with this data. So that's all about this lecture. Thank you for your interest on this topic.